Mr. Benson here with a video going over the second set of questions. I'm splitting this into three so I can get them out a little bit more regularly. Sorry, I actually am really struggling to get this stuff done due to my eye. It's making it a bit harder for me to kind of get through these as quickly as I'd like. Okay, so first question that we're looking at is a titration question. Now, the only real difference is that this is about sulfuric acid, and what we'll be looking at in the SAC and the exam is more about organic acids and other organic substances that we can titrate with. Now we want to find the concentration of sodium carbonate solution, which is our primary standard solution. Now what we know in this case is we know that our mass of sodium carbonate is 2.65 grams. We also know the volume of the solution. Now the first thing we need to do is we need to get our number of moles. So N is M over big M. So we've got 2.65 grams and the mass of sodium carbonate is about 106. This gives the nice round number of 0.025 moles. And then to get our concentration, C is N over V. So we're just doing 0.025 over 250 times 10 to the minus 3 because we've got to be working in litres. And we get a concentration of 0.10 moles per litre. Now, in fact, we could probably go a third significant figure on this one, because if you think about your question, you've got three significant figures here, you've got three significant figures here. So it's probably worthwhile working with three significant figures for the whole solution. I'm not going to do that because this is just an example. Next, write a balanced equation for the complete reaction of the sodium carbonate and the sulfuric acid. Now this is one of these times when you've got to remember your basic acid-base reactions. You'll see, acid plus base is salt plus water. This is a slightly different one. Acid plus carbonate is salt plus water plus carbon dioxide. So we've just got to write down what we've got. So sulfuric acid, H2SO4. Now our states are always essential in these. It's assumed that you're going to get them right. Now it's in solution, so it's aqueous. Plus sodium carbonate, Na2CO3, also aqueous in this case. Then we get our salt. Salt is just going to be sodium sulfate, so Na2SO4. That will also be aqueous because all sodium compounds are aqueous, plus carbon dioxide, gas, plus water as a liquid. Okay, so the first group took a 10 ml aliquot of the 2 molar sodium, 2 molar acid, and dilute this to 250 ml in a volumetric flask. It's placed in a burette. That's really odd. Because, okay, so this might be a question later on, but normally you would put your standard in the burette and you would put your unknown in the conical flask. So this is a little bit weird already. So taking 20 ml aliquots of the sodium carbonate, placing it in a conical flask, add a suitable indicator and titrate with the acid solution. So yeah, that's not actually usually how it's done. But anyway, what we've got is the average titer of the acid solution is found to be 21.61 ml. But all we've got to really think about here is stuff that we know. Now, this is an unusual situation because they're telling us the average titer here, but this is actually the volume of the unknown solution. So this bit of information is going to be one of the last things that we deal with. So what we've got to think about is what we do know. And what we do know is our standard solution. So we took 20 ml aliquots of the standard solution. What we've got to think about is our number of moles of sodium Na2CO3 is CV. Now our concentration was 0.10 moles per litre, and then it's times 20 times 10 to the minus 3. So this gives us, well, I'm just going to make that 2 times 10 to the minus 3 mole. Again, should have some decimal places after the 2, but I'm just leaving it for this simplification for this sort of example that I'm doing. Now, the next thing we've got to think about is that the number of moles of sulfuric acid equals H2SO4 rather, equals the number of moles of sodium carbonate. We know this from the stoichiometry of our equation that we showed on the previous page. So this is 2 times 10 to minus 3 moles. And then to get our concentration of the sodium, no, actually there's a couple of ways we can think about this. Now this is the amount that's present here. Okay, cool. So the next thing I'm going to think about is I'm actually going to use this 21.6 mil value, because this is the amount of sulfuric acid that was present in 26.1 mils. I think I said that wrong before. So the first thing I'm going to think about is the concentration of sulfuric acid is going to be N over V. So it's 2 times 10 to the minus 3 over 26.1, again times 10 to the minus 3 because we're talking in litres, and we get 0.077 moles per litre. Then what we're going to do is we've got to think about, now this was in our diluted solution, but this had been diluted down by a factor of 25. Now, I don't really care, and no one cares, in fact, how you then do the next step. You could do, you know, C1 V1 equals C2 V2, that kind of stuff, but basically all you're doing is saying that C original is just 0.077 multiplied by a dilution factor, which is 25 times, because we went from 10 mils to 250 mils. So we plug that in, times 25, and we come out at I get about 1.92 moles per litre. Now, this is shown as a 6-mark question on this old STAV exam. Now, look, their marking and stuff can be a bit wacky, but this is a fairly involved question, so a lot of steps to get the marks, so it's sort of about right. Okay, the second group used the same procedure but did not carefully read the label of the acid and used 2 molar hydrochloric acid instead of 2 molar sulfuric acid. Explain how this would affect the average titer. Well, for a start, the main thing that they're getting at here is that the ratios of the moles aren't going to be the same. So if you're using 2 molar sulfuric acid, you know that you're going to be reacting 1 mole of HCl, 2 moles of HCl, so it's going to be 2 moles of HCl to each mole of sodium carbonate. Now what that means is that you're going to basically be using half as much of the sodium carbonate relative to the HCl. The problem with this question, though, in the way that they've written it, which is a little unusual, is that they're actually putting the titer is of the unknown substance, not the known one. So this would actually double the average titer. In most situations, as I said before, you're titrating the standard against the unknown. I don't know why they are doing it differently in this case. So that would be double. Now, third uses the same procedure but inadvertently used a 20 ml pipette to take the original aliquot of 2 molar acid. So basically this is saying that you've got twice as much acid in or twice the concentration of acid in your titer. That is going to halve it. So you've just got to think about your ratios here based on what's going on in your question. Which of the groups, second or third, was unable to easily complete the experiment. Explain why. This is a bit of a strange question. You've got to think about what's going on when you're doing a titration. Now, a burette typically contains 50 mils of liquid. Now, you might remember that the titer in the first experiment was 26.1 mil. Now, if we double that, which the second group would have happened, then so we go times 2. This is greater than 50 mil. So the second group would have had more trouble. So it is the second group. And the reason for that is that they would have needed to refill the burette. Now, this is not horrible. But if you do that in the middle of a titration, it increases the errors that you experience. Okay, then we're getting on to a fats question. So linoleic acid, C18H32O2 is an essential fatty acid. How many double bonds does it have? Explain your reasoning. Okay, so if it's got double bonds, it means it's unsaturated. Now, if you think about a saturated fatty acid, well, what do they look like? They've got H, O, C, and then after that, they've got CH2, CH3, that kind of thing. So if we think about a fairly simple structure like this, so this has got C3, H6O2. So we've got C3, H6O2. Now, if we added another CH2 in here, we'd get C4H8O2. So when they're unsaturated, it should always be a 2-to-1 ratio between the H's and the C's. Now, when we look at linoleic acid, it's C18H32. Now, if it was unsaturated, it would have to be H36. So that means that it's missing 4 carbons, so 4 hydrogens, sorry. Now, this means that it is 2 double bonds, because each double bond, causes 2 less carbons. I really don't know why this is so laggy at the moment. Okay, bromine can react with linoleic acid. What kind of reaction occurs between bromine and linoleic acid? So this is actually going back to our straight organic chemistry stuff, but we're thinking about the bonds that are present. If it's got double bonds present, they can undergo addition. So we can just add bromine into the double bonds on the linoleic acid. Determine the mass of bromine which reacts with 10 grams of linoleic acid. So what we've got to think about here is, well, firstly, the number of moles of linoleic acid in 10 grams. So this is just N equals 10 over the mass of linoleic acid. Now, all you've got to do is just add up the masses of, the numbers of carbons and hydrogens and oxygens and what have you, and you get about 280. So the number of moles of linoleic acid, just 10 divided by 280, is 0.036 moles, or thereabouts, 0.036. Now, what we know is that there's 2 double bonds, so there's going to be 2 bromine molecules reacting with each molecule of linoleic acid. So it's a 2-to-1 ratio. So NBr2 is going to be 2 times 0.036, which is times 2, 0.071. And then all we've got to think about is the mass of bromine is 0.071 multiplied by the molar mass, which is 160. And we get our answer there. So multiply that by 160. What I tend to do when I'm doing these is you leave the previous answer in your calculator, and you tend to just use that in your next calculation. Okay, explain why linoleic acid has a lower melting point compared to stearic acid. So we learned a little bit about that one. So we know that the unsaturated fats, and also that they're generally cis unsaturated fats. So cis unsaturated fats we know that they don't pack together because the molecules form well, basically have kinks in them that are not flexible due to the double bonds. And so what this results in is decreased dispersion forces, and that results in a decreased melting point.